Picture trying to build the future with nothing but boxes of punched cards, your code locked out of sight behind glass, and one drop deck turning days of work to chaos. For computer programmers in America in the 1970s, prestige came with pressure, and mistakes could cost entire nights. Why did the digital revolution begin in such a fragile, physical world? How did anyone survive it? Inside a typical computing center in the 1970s, the first thing to hit you was not the technology, it was the architecture. Mainframe computers such as IBM System 370 sat on raised floors behind glass walls, humming in their own climate-controlled world. The air was kept cool and dry, not for comfort, but to protect the machines from dust and static. Programmers rarely set foot in these rooms. The computers were visible through thick windows, but access was restricted to operators and system staff. This separation was not just about security. It was a line drawn between those who managed the machines and those who wrote the code. Most programmers spent their days in separate offices or shared workspaces, sometimes down the hall, sometimes in another building entirely. Desks held boxes of punch cards, stacks of coding sheets and reference manuals. The only connection to the mainframe was through physical media, a deck of cards, or a stack of forms. To run a program, you did not simply walk up to a computer and type. You walked your card deck to an operator station, or passed it through a submission window, and waited for your job to join a queue. The glass partitions and locked doors were not just about protecting expensive hardware. They shaped the rhythm of work, turning programming into a process of handoffs and waiting. The machine room was a controlled environment, but for programmers it was also a reminder that the real power and the final say always sat on the other side of the glass. A punch card deck was not just a stack of paper. It was the physical embodiment of hours, sometimes weeks, of work. Each card held a single line of code or data, and the order mattered more than most people realized. In many shops, a keypunch operator took a programmer's handwritten coding sheet and carefully typed each character one at a time into the IBM 029. The machine's clatter filled the room as holes were punched in the heavy card stock. But speed was not enough for critical jobs like payroll or billing. A second operator would run the deck through again in verify mode. She would retype every character, column by column. If even a single keystroke did not match the holes, the machine stopped cold, a red error light flashing. That extra pass caught the errors that could bring an entire company's accounting to a halt. Most programmers learned to check their decks themselves, thumbing the edge to make sure the sequence numbers in columns 73 through 80 formed a perfect staircase. Those numbers were a lifeline. Drop a deck in the hallway, and if you were lucky, you could reorder the cards by those digits. If not, you faced the slow agony of reordering by hand or starting over completely. Rubber bands and card boxes became essential tools, not just for organization, but for survival. One operator, remembered for her sharp eye, once caught a mispunched digit in a production deck just before it went to the reader. That catch saved a weekend's worth of reruns and averted a payroll disaster. For everyone in the room, it was a reminder. The smallest slip could mean a lost day, a ruined job, or 100 people waiting for their paychecks. Deckcraft was discipline, anxiety, and pride, all pressed into 80 columns of cardboard. Late afternoon brought a quiet race against the clock. Programmers lined up at the operator window, clutching their card decks and job control forms, eyes darting to the wall clock and the growing queue. Each submission joined a stack of jobs, sorted into trays marked by class, Class A for payroll and billing, Class C for student code, and test runs. Priority was not just technical, it was social. Operators knew who had a deadline and who was just running another round of test code. A well-timed favor, or the right word to the night shift, could sometimes bump a job up the queue. Machine time cost money, especially during business hours. Overnight, the rates dropped, and the competition thinned out. Some programmers learned to work the system, submitting big jobs just before the evening cutoff or staying late to catch the start of the cheaper window. A few, like the systems programmer who always seemed to have a printout waiting at dawn, made a habit of negotiating with operators for a late-night class bump, trading a cup of coffee or a quick fix for a spot in the next batch. Desk-checking code became a ritual. With only one shot at the queue, every line on the coding sheet was reviewed, every logic path traced out by pencil. One typo, one misplaced character, and the job would stall in the queue, only to come back with a single error message, sometimes 12 hours later. The cost was not just time, it was knowing that everyone else in line was waiting too, and that a single mistake could mean losing your place in tomorrow's run. By the time the sun rose, the printout bins told the story, who had made it through the night, and who would be back in line, card deck in hand, ready to try again. COBOL read like a set of instructions for a careful clerk. A programmer would write, "Move hours in to hours out," and the card would capture each word, one per line, 80 columns at a time. The verbs were plain: ADD, subtract, perform. Business rules were spelled out in blocks with data divided into neat sections, no abbreviations, no tricks. That clarity made COBOL the language of payroll, billing, and insurance. Across the hall, a Fortran programmer attacked scientific problems with a different rhythm. Here, the code was dense, almost mathematical. An example looked like do 100i equals 1 through 10. Loops and arrays, columns lined up just so. Fortran cared about the position of every character. A label in columns 1 to 5, a continuation in column 6, code from column 7 onward. One misplaced digit, and the compiler would choke, sometimes with nothing more than a cryptic line number on the printout. Assembly language was another world entirely. Systems programmers spoke in OP codes, like the letter L for load, the letters ST for store, and the letters BNE for branch if not equal. Each instruction mapped directly to a memory address. Mistakes here could crash the entire system, not just a single job. Manuals were always open, blue reference cards tucked in shirt pockets, because every opcode and register mattered. Debugging was an exercise in patience and detective work. When a program failed, the mainframe printed out a dump. Pages of hexadecimal numbers, addresses, and register contents. A systems programmer would run a finger down the memory dump, matching addresses to variables, looking for patterns, a stray value, a pointer gone wild. Sometimes the only clue was a string of numbers where a name should be, or an address pointing just past the end of an array. The fix often meant pulling the right card from the deck, repunching a single line, and waiting another day to see if the bug was gone. Every language had its own rituals, but all shared the same constraint. The printout was the only window into what the machine had done. Landing a programming job in the mid-1970s meant stepping into a world of steady paychecks and clear advancement. A starting salary of $14,000 to $18,000 a year put you comfortably above the national median, enough to buy a house, support a family, and plan for the future. Senior programmers and systems analysts could pull in $25,000 to $30,000 a year, with defined benefit pensions and health insurance as standard. The benefits matched those of engineers and managers, including group medical, paid vacation, and even subsidized cafeterias in the big offices. But the doors didn't open for everyone. Women, who once made up a large share of the field, were increasingly pushed toward lower-paid roles like keypunch operator, with slimmer benefits and little chance to move up. IBM's dress codes, and business-like culture made it clear who belonged in the professional ranks and who didn't. For those inside, it was a secure, respected path. For many others, it was a locked room. Tape reels snapped mid-run, spewing brown ribbon across the floor. Card readers jammed without warning, sometimes chewing the first 10 cards of a deck before an operator could react. Fatigue set in as programmers watched the clock, knowing a single hardware hiccup could erase a night's work. Logs filled with notes. Tape error, job rerun. Disk fault, CE called. Reader jam. Cards damaged. The cycle wore people down. Hours lost to mechanical quirks, waiting for the next available slot. Then, almost overnight, a new sound replaced the clatter of cards, the quiet click of a terminal keyboard. The first time a programmer typed a line at a DECPDP11 and saw results in minutes, everything changed. No more waiting for tomorrow's printout. A systems programmer later said that the first terminal felt like someone opened a window in a locked room. Today, code lives in the cloud, instantly shared and endlessly copied. But every seamless tap rests on decades of invisible labor and discipline. The world runs on software, yet true understanding of its origins fades. What we automate now, they built by hand. Their precision still shapes our digital reality.